Hello, my name is Cole Prashant, and I'm a fifth year honors student in the University of Utah School of Computing and Department of Mathematics. Over the last 3 semesters, I've done research analyzing the performance of different graph algorithms, specifically those used in the structural rounding framework first introduced by Eric Demain in 2018. I did this research through the Theory and Practice group under Professor Blair Sullivan. Structural rounding on parameterized classes using heuristics. Let's start with a little background. So when I say graphs, what do I mean? Well, in computer science, a graph is simply a data structure we use to represent connections. A great example of this is shown in pathfinding problems. Say you just booked yourself a COVID-19 vaccination appointment in Sandy, Utah. If you live in Salt Lake City, you might not know the fastest or most direct route there off the top of your head. This is where pathfinding software like Apple Maps could help, but how does Siri do it? Well, if you consider intersections as vertices or dots, and the roads connecting them as edges or lines, then it becomes clear how one could trace instructional paths to our destination. Representing the data this way also allows us to formally define our problem and to start looking for optimal solutions. Algorithms for optimal solutions, however, are usually difficult to compute, often to untenable measures. To show this, let's take a deeper look at the problem of dominating set. A dominating set in a graph is just a set of vertices from the graph whose edges touch all of the remaining, unincluded vertices. If our graph were a social network where our vertices represented people, and edges between them represented friendships, we could think of a dominating set as a group of people who are friends with everyone in the network. Finding such a group is easy. We could just pick all people to begin with. Since everyone is covered, our set would vacuously be a dominating set. Say instead then that we want to find a dominating set with the smallest amount of such people from the group as possible, our social superstars. Minimum dominating set, as it's defined, is much harder to solve and is an example of what we call an optimization problem. On general graphs, minimum dominating set is non-deterministic polynomial time solvable, or NP for short. This means that, with the exception of very small graphs, finding an exact solution would take much too long. In fact, when run on modern computers, if your network has more than just 100 people, your program would likely take several years to complete, if at all. Sometimes, however, different graph shapes can lead to significant algorithmic advantages. Say this network was instead a family tree as shown by the figure in the right. Minimum dominating set becomes exponentially easier to solve in this scenario, and even has exact solutions better than polynomial time, p. Thus, it can be advantageous when data is well structured. The question is then, how structured is most real-world data? And the short answer is, it depends. For most domains, it's almost never the case that we get rigid structure from our data initially. It's more often than not noisy and full of exceptions. To show this, let's define what I mean by noisy. To understand noise in a graph, we first have to determine the structure we wish to see. There are many kinds of structural classes a graph can adhere to. We'll use again our previous example of trees, where every child node can have only one parent. This time around, highlighted vertices signal where the fewest number of vertex deletions we need to occur in order to represent our original graph as a tree. We can think of noise then as these removed vertices that otherwise distort our graph from being structured. Structural rounding is based on an earlier idea similar to this, that imagines a true version of the graph lying within the original. The edits, i.e. vertex or edge deletions required to get there, are considered the extra noise. What we now want to think about is how hard it is for noisy graphs to be edited to structured ones. There's some good news here. Network science has empirically established that real-world networks, social, biological, computer, etc., exhibit significant sparse structure. Sparsity, which is the measure of how few edges there are on a graph relative to its vertices, is integral to the structural rounding hypothesis, which states that most real-world graphs are close to structured, such that if we know there's an internal structure in our graph, and that our graph has few connections, editing to get there is relatively easy. The framework for doing so is pretty intuitive. Structural rounding is a 3-step process: edit, solve, then lift. We'll use the problem of vertex cover on bipartite classes to illustrate. We can ignore the details for now. As we saw before, we start with some real data as an unstructured graph and want to edit it into a structured class that would allow us to solve our optimization problem faster and/or more accurately. Once there, we solve, then finally lift this solution back to the original graph. This new operation, lifting, simply means identifying those same solution vertices, only this time within our original graph. With all of our vertices back together again, we can see if our solution still satisfies the problem. If not, there are clever methods we can use to create complete solutions by adding some of these ignored vertices that we previously considered noise into our solution. This added solution portion is colored blue in our figure. The extra editing and lifting steps limit our final solutions to approximations. This means that we're not exactly optimal, However, our worst case performance can be determined by structural rounding, which we'll illustrate later. Moving on to the literature. The original paper established a plethora of different problem class combinations that are amenable to the framework. To that extent, several of these problems also achieved better approximate solutions in the worst case, beating out world's best competitors at the time. These are strong theoretical results. But while exciting, the majority of these combinations have yet to be implemented and tested on real-world data. It's still to be determined whether structural rounding wins in the average case on many of these problems, as well as if it has faster runtimes. Illustrated below is a collection of some of these problem class combinations, itself represented as a bipartite graph. Bipartite just ensures that the graph's vertices can be segmented into halves with edges connecting the two sides, like a word matching game, except that here, words can match more than once. Prior work done on structural rounding includes the framework's first real-world evaluation, which was done by members from the Theory and Practice group. Back in 2019, they put to the test the problem class combination of vertex cover on bipartite graphs. A vertex cover is similar to a dominating set, whereas a set of vertices representing a dominating set must reach all other vertices in a graph, a vertex cover must reach all edges. From our earlier social network example, where all friends had to be reachable, vertex cover ensures that all friendships are reachable. The problem of vertex cover has several algorithms that give two approximations on general graphs. These were structural rounding's competitors. A two approximation means that, in the worst case, solutions will be a scale of at most 2 away from exact. So if the size of a graph's optimal solution for vertex cover is 10, the solution to a two approximation algorithm would return a cover of size at worst 20, or twice larger than optimal. Seen below are solution quality results from the paper, testing structural rounding in blue against the best performing two approximations in red on a real-world corpus. The y-axis can be thought of as the obtained average case solution qualities when run on each graph, where one represents optimal and larger is worse. The x-axis then can be thought of as the amount of the graph that was in the edit set, where 100% represents the entire graph had to be edited. Intuitively, these results make sense. Graphs with smaller edit sets are closer to structured classes. Thus, the extra effort in editing and later lifting is minimal, and furthermore is rewarded with better overall approximations, since there is an efficient exact solution to minimum vertex cover on bipartite graphs. Thus, as you can see, structural rounding wins big on solution quality. Runtime, however, was not as convincing, coming in at about 2 to 3 times slower than the two approximations on average. This work helped us determine what we wanted for our current project. Vertex cover was an easy problem. It had good approximations on general graphs already, and an exact solution on bipartite. For our next paper, we wanted to try and solve something a bit harder. We've also talked about a couple of structural classes so far, trees and bipartite graphs. These classes are considered binary. Either a graph is a tree or it isn't, right? Parameterization adds an extra integer value to such structural classes. Its value roughly measures how close our graph is to being some binary class. Since parameterized classes are covered in the literature, we thought it would be important to test how their tunable structure could affect our performance in the real world. Lastly, editing is what slowed us down in prior work. We wanted to investigate if there was anything that could be done to speed up this step. Further, our work evaluating different editing methods in vertex cover suggests that using the editing approach which gives the smallest possible edit set is important to achieving a better solution quality. So we wanted to ensure our editing still achieves small edit sets. We arrived at the problem of minimum dominating set on bounded tree width. Hopefully by now you have a good idea of minimum dominating set from our earlier examples. As a reminder though, MDS is an NP-complete problem which wouldn't terminate on general graphs. We also talked about how this problem became easier to solve on trees. Because of this, bounded tree width was a great choice for our parameterized class. Tree width tells us roughly how close our graph is to being a tree, and is defined in a few equivalent ways. For the purposes of this presentation, we want to think about a graph's tree width as the smallest maximum bag size found in its tree decomposition. Not to get too technical, a tree decomp can be thought of as a condensed version of a graph, where previously connected nodes are concatenated into single nodes called bags. The size of these bags ultimately determines a graph's tree width. The figures below illustrate a tree decomposition where a maximum bag size is 3. Smaller values represent being closer to trees, thus this example is very close. Done as an extension to our current paper, and as a result of early data, I wanted to explore some further reaching modifications of the structural rounding framework. For context, when editing to parameterized class, there are two important values to consider: initial and target. For bounded tree width, initial tree width k is the tree width of our original graph. Our target tree width t is then how close to a tree we choose to edit our original graph to be. For my thesis, I've chosen to explore the effects of target tree width for a few reasons. First, a smaller target tree width requires more editing to achieve, which would slow us down and could worsen our solution quality. However, the runtime of our exact solution is exponential relative to the tree width, such that a larger target tree width would hurt us considerably more on the runtime of our solve step. Ultimately, since our edit set sizes only increase at some sub-exponential rate as we lower our target tree width, the runtime advantages achieved by optimizing for our solve step should outweigh the solution quality degradation that we'd experience. From a runtime perspective then, it's easy to imagine an upper limit for target tree width if we want structural rounding to be competitive, speed-wise. I was curious to see how these fragile ideal target values related to our initial tree width values on real-world graphs. This is all in the hopes that I might discover a formula for deriving the best target tree width to edit to for any graph. To remove our runtime burden of editing, I also wanted to explore the potential effects of heuristics. The worst-case solution quality guarantees that structural rounding provides go out the window when heuristics are used, so it's important to investigate the average-case solution quality of structural rounding's solve step in these scenarios. On to my contribution. To answer these questions, we needed very specific graph data. The only way to obtain such graphs was to build our own synthetic graph generator. Thus, one of my most significant engineering contributions was that graph generator. Developed in C++11 over the course of several months, I used the existing structural rounding graph library we'd previously developed, as well as a popular third-party graph library, iGraph. iGraph has a method to sample proof or sequences uniformly, then converts them to trees. I used this method, then shaped these trees into randomized graphs. Apart from number of vertices and edges, we're also able to control a graph's initial tree width, their edit set size, or how far away they are from being structured, and their sparsity, or how few connections the vertices have. Okay, so we know that an approximation is just a measurably imperfect solution to a problem. Well, parameterized classes present a unique opportunity that is similar to this during our editing step. Since bounded tree width is not a binary class, we don't have to edit exactly for our solve step to work correctly. In this way, we can edit heuristically. Like an approximation, a heuristic gives us a less than exact solution and in turn grants us a dramatic runtime improvement. However, heuristics differ from approximations by providing no guarantees on the worst case behavior of their solutions. The trade-off here is that the speedup can be phenomenal. So even if we only use them in the editing step, our entire SR approximation comes crumbling down. But that might not matter if average case performance improves. The rationale behind using them in this research is that we already know structural rounding performs well in sparse graphs where we don't do a lot of editing. Since editing has been our slowest step, and since we'll have to do more of it to get to optimal tree width values, I wanted to implement a fast editing heuristic to try to make structural rounding amenable to graphs as dense as possible. I chose to explore this editing pursuit using greedy degree, one of the fastest heuristic bounded tree width algorithms, which was defined in an earlier Bodlander paper. Another of my significant engineering contributions is found here, in developing this method for our library. The other editing method we are considering uses balanced separators to find tree decompositions. Initial results are very surprising. Our greedy method was much faster and found smaller edit set sizes on synthetic graphs, as predicted, but actually produced worse solutions. How is this possible? This goes against what our previous editing results from Vertex Cover suggested. It's possible that greedy degree produces worse tree width bounds relative to our separator-based method, meaning it could be overestimating the bounded tree width during editing, which in turn could be producing these smaller edit sets. The loss in solution quality is still unclear, but greedy degree's decomposition inaccuracy is believed to be the leading cause. What's also is that our generated graphs were assigned target tree width values based on knowledge about their underlying structure. Actual structural rounding should probably guess here or try to make multiple values work, as it wouldn't know these values for real-world graphs. So, more to be done. It still remains to test what target values structural rounding should attempt to edit to on real-world graphs. Lowering our target might allow us to now take advantage of greedy degree's observed smaller edit set sizes. Since getting to a smaller tree width would require even more editing, I think there's still room here to win, even if greedy degree is overestimating. In the other direction, when increasing our target tree width, because of the exponential increase in solution time, it's likely there's a hard upper bound we still need to find. Thus, there's more to explore about this target tree width sweet spot than was previously expected. It will affect both runtime and solution quality. Results on bounding this target value will follow in my senior thesis to be published later this month. A question for another paper might be identifying where else we can use heuristics in structural rounding. Since we've already lost our worst case guarantees, maybe we should plug heuristics into the other steps of the pipeline as well to get a more competitive runtime. I'd like to thank my faculty mentor, Dr. Blair Sullivan, Associate Professor in the School of Computing. Her mentoring and overall involvement on this project have been crucial to my work, and I've been very fortunate to have her as my honors thesis advisor. I also want to thank 2 doctoral students from my team, Brian Lavalley for his mentoring, and Madison Cooley for providing research materials. Special thanks also to the University of Utah's Office of Undergraduate Research and to the Gordon Betty Moore Foundation for funding this work in part. Finally, if you wish to implement this code yourself or contact me with any questions, I've provided details below. Thank you for listening, and I hope that you enjoy the rest of your day.